Hello everybody. In this presentation, I want to give an overview of genetic algorithms. So the field of genetic algorithms was developed by John Holland at the University of Michigan in the early 60s. So they have been around for quite some time. Genetic algorithms, or GAs, use evolutionary principles to evolve solutions to problems. They are known as one of the most powerful optimizer there is. And among others, we want to have a little bit of a look at how they represent knowledge. So let me give you an example. This example is from the Wikipedia entry on genetic algorithms. This is an antenna that was developed by NASA to increase, I think, diffusion. And so you sort of look at this thing and say, wait a minute, it's just a paper clip that somebody bent and soldered to the top of this plug over here. No, according to NASA, this one was evolved by a genetic algorithm. Here's another example. Next time you're in an airplane, you may notice those winglets here at the end. And so the winglet shape is being maximized to reduce drag. And they use, some of the airlines or airplane makers use genetic algorithms to determine the exact shape. So those are two examples of genetic algorithms. So how do they work? So let's have a look at this black box over here. It has 5 toggle switches, on, off, on, and off, and it produces an output signal. This example is, by the way, from the book by David Goldberg entitled Genetic Algorithms in Search Optimization and Machine Learning. The book has been around a little bit, so you can get used copies very, very easily at a very low cost. So the idea is we flip these switches a certain way, and we observe an output signal. We now have to rate the output signal, and we call this thing a payoff. And we are probably interested in maximizing our payoff in this example. So we're sort of like trying to figure out, flip the switches, which configuration gives me the highest output signal or the biggest payoff. And that's what we want to do. We want to optimize the payoff. Now, a genetic algorithm can do that without ever cracking open the box. It doesn't have to know anything about the inner workings of the box. It doesn't need to know which function this box computes. So this is the example that we're going to work with to figure out how these things work. So the first thing we need to worry about is how to represent the input. Well, there are 5 toggle switches. They're either on and off. So we're going to use a string of 5 bits. And so this particular example might be represented as 1, 0, 1, 1, 0. And so we call this thing a chromosome. So now the first decision we have to make is how many chromosomes do we have? And that's called the size of the population, the size of the population. So and this decision is being made by the user. So they decide, how big of a population should we have. We'll have a look at some examples later on where we can give some sort of informed input on the size of the population. But for now, we're just going to make it 4. So we're going to have 4 chromosomes, and if we decide to do that, and we know each chromosome is 5 bits, then we simply fire up our random generator and generate 20 bits. And so random generators are used quite a bit in genetic algorithms. So here are then the 4 chromosomes that we get. Now, genetic algorithms or genetics is all about mutation and crossover. So how do we do that? So we're primarily considered about crossover. So the first thing we're going to do is we determine the output signals of each of these 4 chromosomes. So here are the output signals: 169, 576, 64, 362. Now we're going to be measuring 3 things, but 2 things are really important to us, and they help us assess the quality of the population, and more importantly, whether we're getting better. So we're looking at the max, which is 576, and we're looking at the average. Now it turns out we're actually much more interested in the average than the max, because we know that the higher the average, that means we have a much better quality population, and the higher the quality of the population, the higher the chances are that we're going to get a really good max out of this thing. And so we can use these things as a termination condition. So if the average doesn't go any higher, or if the max doesn't go any higher after a few rounds, then we may sort of say, well, let's terminate. But another way to terminate is to simply run this thing for a given number of episodes, if you wish. So I said crossover is key, and in order to do that, we need to determine which of these chromosomes get to go to the mating pool. And then at the mating pool, we do the crossover. So the idea is, if we want to increase the max and the average, we probably want to have chromosomes that are high performing make it to the mating pool. And so this one here probably should make it, this one should make it, and this one should make it. This one probably not so much. It's really much, much less than this one over here by order of magnitude. So how do we determine that? Well, the lest you think that people in GAs are boring, they use a roulette wheel. Again, more randomness, even some hints of gambling here, right? So what we do is we take our roulette wheel and we indicate, maybe we'll paint portions of it corresponding to the performance of these chromosomes. So here's the third metric that I mentioned. We're going to take the sum of all of these output values. And so then we sort of like simply divide the value of an individual chromosome by the sum. And so we get 0.14, 0.31, 0.06, and 0.49. And so now what we're going to do is we're going to take these values and so like, use them to determine aspects of this roulette wheel. So this chromosome gets almost half of the roulette wheel. This one gets about a third, and this one here gets 0.06, and this one here gets 0.14. And now what we're going to do is we're going to spin the roulette wheel 4 times. So we don't increase the size of the population or decrease it. And so we're going to spin it 4 times. And as you might expect, this one should probably, the little ball should land on this portion twice, about twice. Again, it's all random, right? Probably once, maybe twice, and probably once, and probably not at all over here. So that's kind of like what we expect. So in other words, if we run the roulette wheel 4 times, we multiply these numbers by 4, we get 0.58, so 1.97, 0.22, 1.23. So probably twice over here, once over here, and maybe once over here. But we don't know. So we do this thing, ta-da, and here are the results that we come up with. So again, this is entirely random, and this is a little bit massaged towards this example. We're going to learn something about these things. So it turns out this one here gets to go to the mating pool once. 2 copies of this one get to the mating pool, and 1 copy of this one gets to the mating pool, and this one does not get to the mating pool. All right, so what's next? Yep, I set it over here. So now we need to determine who gets to mate with whom. And again, we use a random generator to determine that. And so in this particular example, it turns out that the top 2 get to mate, and these 2 get to mate. So the next thing we need to determine is the crossover site. And again, it's randomly determined. So here are, again, the examples from this book that, we have a crossover site over here and a crossover site over here. So now we actually do the crossover. So notice we have 0, 1, 1, 0, 0 over here, 1, 1, 0, 0, 1 over here, 1, 1, 0, 1, 1 over here, and 1, 0, many zeros over here. So now we have a new generation. So great, let's figure out how well we did. Let's figure out whether we improved things. So we're going to evaluate this new generation, and here are the values. So we have a new max, 729, and the new average is 439. So here are the old values. So compared to the old max, we significantly improved it. And most importantly, compared to the old average, we significantly improved that one also. So the performance of the pool has increased according to both dimensions. And so that's one run through the genetic algorithm. So now we're going to do the same thing as before, determine the percentages that each of these chromosomes contributes to the overall quality, and use a roulette wheel, and so on and so forth. So what are some modifications that people do? What are some sort of like variations of GAs that one can do? So I already mentioned to you that we kind of have 2 primary choices for termination. We simply can run it for a certain number of iterations and so like take what we get, or we can run it until the performance increase goes below a certain delta. Maybe nothing changes for several generations. I haven't talked much about mutation, but what we do is if the mutation rate is, 20%, then every fifth bit gets flipped. Okay, if the potential rate is 1%, obviously every 100th bit gets flipped. So no big deal over here. The biggest variations in GAs come from determining who gets to the mating pool. And there are many approaches that people use. One of them is called elitist, where the top performer always gets to mate. And a variation thereof is that the top N performing chromosomes always get to mate. Some variations even go so far as guaranteeing a spot in the next generation for the top or top N chromosomes. So it's just all, if you were to use them, you sort of need to try some of these things and see which one gives you the best solution. Another variation is, you not simply toss those top-end performers into the mating pool. You actually make sure that whenever you mate, one of the mates is a top performer. So many different ways of doing this thing, but the good old vanilla variety of genetic algorithms actually works really well. The next thing we want to look at is the traveling salesperson problem. We know it is exponentially complex, so for any reasonable problem instance of these things, we can't find an optimal solution through search. Now, genetic algorithms are not guaranteed to find an optimal solution. They are an optimizer. However, they are extremely competitive. It appears that whenever somebody develops a new optimization technique or algorithm, when they evaluate it, they always compare them to GAs. They're sort of real stable. You always want to catch those GAs. So the traveling salesperson problem is a little bit more complex. So suppose we have 10 cities labeled 1 to 10. So here are potential tours, 9 to 8, 4, 5, 6, 7, 1, 3, 2, 10, and here's another one. So let's go ahead and do this the wrong way. So we choose a crossover site, like say this one over here, and so we get two new tours, right? 9, 8, 4, 5, 3, 10, 9, 5, 4, 6, which we have over here. And as you immediately see, wait a minute, we have duplication over here and duplication over here. Among others, 9, 9, and then we have the same problem over here. So clearly there are cycles and we're missing some cities. So this doesn't work. So we have to come up with a better solution. So John Graffenstetter and some of his students, I assume, developed a really interesting solution. They use two crossover sites. And so again, determined at random. And then they use the information between those two crossover sites as a guide to modify the original solutions. So long story short, they will, in both of these chromosomes, exchange 6 and 3, 7 and 10, 1 and 9. 6 and 3, 7 and 10, 1 and 9. So let's have a look at how that works. So we're going to, let's say we start with this one here over again. And so 6 and 3 are going to be exchanged. So you will see that the 3, 10, 9 goes up and the 6, 7, 1 goes down. But again, we'll do some other things here. So what we're technically doing is the 6 and 3 get exchanged. So this 6 becomes a 3 and this 3 becomes a 6. Ta-da! This 7 gets to be a 10 and this 10 gets to be a 7. And this 1 gets to be a 9 and this 9 gets to be 1. So that's the first chromosome, and the same thing down here, the 6, 7, 1 moved down, but in that process, this 3 became a 6 and this 6 became a 3. This 10 became a 7, and where's the 7? This 7 became a 10, this 9 became a 1, and this 1 became a 9. So now we have two valid tours. So we, again, we evaluate those tours. We use those values in the same way we have seen for that black box. To determine a mating pool, and we have seen over here how we do crossover. How do we do mutation in this context? Well, ever so often we randomly flip two cities. So if we have 9, 8, 4, 5, 6, 7, 1, 3, 2, 10, we simply flip 1 and 8 around. Okay, that's how we do this thing. So this is how we guarantee that there are no cycles and we actually cover all cities. All right, so you think that's pretty cool, but wait for the next solution. So now we're going to have a look at a greedy crossover and a greedy mutation operator. So here's what we're going to do. Again, it's the same. I think it's the same cities, and we have two. Again, we have two chromosomes, two tours, and we need those things. And what we're going to do is we're going to determine two new ones. But in this demonstration or this exposition, I'm only going to do one. But we need both of them. So in greedy crossover, we won't determine crossover sites, not one, not two, not three. Instead, we pick a start city at random. So suppose we pick 5. Okay. Now we look at the successors of those cities in both chromosomes. So in this one it's 6, in this one it's 4. Okay. So we pick 5. We look at both chromosomes, and we look at the successor city, which is 6 in this one, 4 in this one. And we're going to create a new one starting with 5, and then we pick the one that actually has the lowest distance. So suppose it is 6. So we start at 5, and then the new one that we're going to do is 6. Let me see whether I can put that in here. So I'm just going to create a new tour. Let me use a different color. And so we start out with 5. And suppose, again, I think 4 is a cheaper one. So we pick this one. So now we're going to continue with 4. So we look at 4 in both instances. And so 4 has a successor of 5 over here and a successor of 6 over here. Now notice we can't take 5, so we're going to take 6. Okay, so that's what we do over here. We look at the successor in both parent chromosomes. We pick the one with the lowest distance, and that's what we did for the first time around. The second time around, we would have created a cycle if we had picked 5, so we pick 6 instead. So now we look at both of them, 6, 7. If we're at the end, we roll around. So we look at 7 and 8. Which one is the shorter one? So suppose it is 7. Okay, so we do that one. Now we look at the successors of 7 in both of them. It's 1 and 1. So notice apparently this is a really good combination. So 7 and 1 appears in both of them. That's something that we want to look at. So we'll pick 1. Then we look at 1. We have 3 and 2. So suppose 3 is a lower cost, so we pick it. And then we look at 3 in both of them. We have 2 and 10. So suppose it is 10. Now we look at 10. Flipping around goes to 9 and 9. Again, this seems to be useful information, so that's good. When pattern develops, that typically means that we're on the right track. So 9, we now have 8 and 5. We have already seen 5, so suppose 8 is actually the lower cost. Then at 8, we look at 4 and 7. So notice that now something interesting happens. Item 5 happens. We have seen both of them already. So 8, 4 over here, which is there, and 7 over here, which is here. So we have to, in this particular example, randomly pick a non-selected city. And I think the only non-selected city is actually 2, right? So let's pick that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. So there you have it, greedy crossover. And we would do that again. Again, pick a random city, use these 2 chromosomes to produce a new chromosome. So that's what greedy crossover does for you. Now, greedy mutation, ever so often you pick 2 cities at random, you switch them. If the new 2 are shorter, you keep the switch, and otherwise you do not keep it. So that's greedy mutation. So there you have it, a run through genetic algorithms. Now let me show you a cool animation for the traveling salesperson applet. So what we have over here is we have, I believe, 50 cities. And this is based on an initial population. The population is 100. Mutation rate is 0.2%. And so this is just a randomly generated tour. And this one happens to be the maximum of the 100 initially generated maximum tours. Notice we have 50 cities. So it appears that for many optimization algorithms, including genetic algorithms and some of the swarm intelligence algorithms, you kind of want to, your population needs to be at least as big as the number of cities for the traveling salesperson problem. And so he doubled it in this particular example. 50 probably would do too. And so let's stop after 10 stable iterations. So again, among all the 100 that he generated, this one happens to be the best initial one. So let's run it. So after each iteration, he displays the optimal solution. Notice that over here, we count the iteration. Over here, we show the path lengths as it decreases. So not much has changed. So we have a path length of 2,601. All right, so that looks pretty good. So let's generate a new population and start this thing again. And so like pay attention to the initial path lengths. I think it was 5,000 or so, 8,000. Okay, so it was above 8,000. So that's pretty good. So last time we had 2,600. Let's see how close we get this time. I think it was 2,610. So that doesn't seem like it's going to improve. So again, I mean, given that we started out with way above 8,000, we got 2,696, and last time we got 2,610. So that's pretty good. You know, can't complain about that. All right, so I wanted to show you now a sort of a pretty cool a genetic algorithm. It's about a genetic algorithm car, where I put car in quotes. So this is just a lot of fun. And so this car, you know, the number of wheels are randomly determined, I think, and the pattern is randomly determined. Here's a track that it has to go, and so you see on the left side they generate a bunch of them, and you know, this one toppled over, so it didn't really make it that far. And so they sort of like talk to you about the distance that they were able to run. So this seems pretty nice. That's a very stable car. So notice that the path gets, excuse me, more complex, more challenging. Whoops. Yeah. So too bad that it didn't do a full 360 there. This is blue one is the one that we've just seen. That was the top performer. So here's a new one. Looks like it's ready to ram somebody. Whoops. So let's see how far it goes. I think the road is always the same. Yeah. So same problem with the pokey one over here. So there you see, so like, you know, the top performer. Oops. Yep. All right. So, okay. So that one, very good. Very good. I think, nice hang time. Yep. Yeah, it's going to get stuck there. Wow, that's a hard one though. And so that was quite a distance over here. So this one should do much better because, having said that, it doesn't have that pokey thing up front. So we know this one is not going to make it. Yeah, sometimes they flip around completely. So again, not enough ground clearance. That one, it doesn't look too bad. A little bit front heavy. Oh, this one looks good. This one looks really good. So it has wheels almost all the way around. So if it doesn't get stuck on the top, yeah, that one should make that one should go. Come on. Having said that, nice to have 3 wheels, wouldn't it? This one is bopping along. Well, in any case, so there's some. It's a fun animation. Don't watch it too much. You can sort of like watch lots of statistics over here. Alrighty, folks, that's it for genetic algorithms. I'll talk to you later. Bye.